Hi folks, this video is on exponential and logarithmic equations. This video is going to focus on the exponential equations and solving them. And it's our first video on our R10 section. So I'm just going to bypass all of the outcomes there. And two things I want to note right off the hop. There are two types of logs that you're going to see more often than the other ones. And they are the common log and the natural log. So the common log, just looks like this, y equals log of x. And there's no number after the log. So if there's no number after the log, it is assumed to be a 10. So I could rewrite this as y equals log base 10 of x. So that's what we call the common log. And then we have the natural log, and this one doesn't even look like it's a log, it just says ln, but that means the natural logarithm. And that actually has a base of e. So y equals log base e of x. And I'll talk more about e later. That's a pretty substantial number when we're thinking about like natural growth or decay and that sort of thing. And so it happens in nature, which is why they call it the natural log. We'll talk more about e later. But ln just means log base e of x. And these function just the same as any other logarithm does. You would sketch them the same, you could manipulate them in the same way. But they're just the ones you're going to see more often. So if I were to sketch y equals log base 10 of x, I do it the same way I do any logarithm. So there's going to be a vertical asymptote on the y-axis, and then I have my basic logarithmic shape. I have a pretty consistent point over here at 1, 0. And then we have one other point, and the x-coordinate of this point is going to be the base of the logarithm, so that is 10, and then the y value is going to be 1. If you have troubles remembering what the coordinates of these points are, you can just remember that logarithms are the inverses of exponential functions. So if we switch x and y here, so we say x equals log base 10 of y, what we can do is we can put this base over the other side and get an exponential equation. So 10 to the power x is equal to y. And then we could sketch that. So now we have our asymptote on the x-axis, we have an increasing exponential function, and we have the constant point at 0, 1. Then if we plug in a 1 for x, 10 to the power 1 is just 1. So we have the point 1, 10. And then because exponential functions and logarithmic functions are inverses of each other, you flip the x and y coordinates. So 0, 1 becomes 1, 0, and 1, 10 becomes 10, 1. We do the exact same thing with our natural log, and I'm going to actually start off by doing the exponential function first. So switch x and y, x equals log base e of y. And then we want to put this into the exponential form. So e to the power x, move that base to the other side, is equal to y. So we have our horizontal asymptote on the x-axis. E is a number that's larger than 1. It's approximately 2.7. It keeps on going forever, but I'll just call it 2.7. And then, so because it is a number greater than 1, we have an increasing exponential function. We have this constant point at 0, 1. Then we have the next point. If we plug in a 1 for x, we have e to the power 1. So x is 1. E to the power 1 is just e. So I would just label it like so. Then if we want to sketch the inverse of that, then we're sketching our logarithmic function. So we have our vertical asymptote on the y-axis. And then we have our logarithmic shape. And then we just switch the coordinates for these points. 0, 1 becomes 1, 0. And 1e becomes e, 1. So the same way we'd sketch any logarithmic function. Next, we get to calculate some logarithms. So here I have this massive calculator to kind of show you how to calculate logarithms, and we get a calculator, so yippee. So to calculate this, I just got to punch in the values on the calculator. So log and then 5. So here's the log button, press that one, then you hit the 5 button, and then hit enter. When you do that, you should get the number 0.6989700043. Now, more often than not, we're going to round these to 3 decimal places. So this is going to be 0.699. So let's try log of 230, or the common log of 230. So again, that's log 230, and then enter. And that should give you 2.361727836. Again, I'm going to round this to 3 decimal places, so we get 2.362. So common logs, pretty easy to calculate. Now let's take a look at the natural logs. So ln of 5, so again, this means log base e of 5. And it's just ln, which is this button right over here. So if I want to evaluate ln 5, I just press the ln, press 5, and then hit enter. When I do that, I get 1.609437912. Round that to 3 decimal places, so 1.609. Now feel free to give this one a whirl by yourself. Again, we have the natural log button, then 230, and we hit enter. So 5.438079309. 3 decimal places, 5.438. And last but not least, we have a logarithm, but we don't have our common log, so the base is not 10. We don't have the natural log, so the base isn't e, but the base is something else. We have log base 2. And when you go to calculate this, at least using this graphing calculator, you can't do it because there's no log base 2 button, and there's no way to write in a 2 as a subscript. So this is really something we can't evaluate as simply as these other ones. However, we can still evaluate them. So if we just set this equal to x, then we can use the little trick by moving the base over to get an exponential function. So 5 equals 2 to the power x. And now I'm going to need some more room to finish this one, so I'm going to move this work down on the page. So 5 equals 2 to the power x. 5 equals 2 to the power x. And at this point, what I can do is I can apply a logarithm to both sides of the equation. Same way you could add 1 to each side of the equation, it would still equal each other. You could multiply both sides by 2 if you wanted, and then it would still equal. So in the same way, I can provide a logarithm on both sides. So I'm going to use the common log just because it's pretty common, I guess. So log of 5 and then log of 2 to the power x. So what was originally in the equation, those are becoming the arguments of the logarithms. If you think back to our last lesson where we talked about the power rule, when you have a logarithm acting on an exponential number, the exponent can be written in front of the logarithm. So that's what I'm going to do. I'm going to apply the power rule. So log of 5 is equal to x log 2. And all along I wanted to solve for x. So to get x by itself, I'm going to divide both sides by log 2. So I have log 5 divided by log 2 equals x. And now I can go back to my calculator and I can calculate log 5. I can calculate log 2, so I can divide those two numbers. And the number you should get is 2.321 2.928.095. You want to round that to 3 decimal places, 2.322. If you keep getting the number 1.220360232, it's because you're making a bracket error when you're plugging this into your calculator. The way I plug it into my calculator is I go log, and then my calculator automatically opens a bracket, but if yours doesn't, I would open a bracket. I go 5, and then I close bracket. Then I would divide, and then I would go log, open bracket, 2. If you want to be super safe, you can put brackets around that whole first thing, but you don't really need that. So if this is the number that you're getting, you're making a bracket error as a mistake. Now let's try the same thing with log base 2 of 230. Feel free to give it a try on your own if you're comfortable with that. Log base 2 of 230, that's going to equal something. We'll just call that x. So step 1, put this into exponential form. 230 equals 2 to the power x. The next thing I did over here was I applied a logarithm to both sides. So log of 230 equals log of 2 to the power x. You could really apply any logarithm that you want, but you really want to apply either the common log or the natural log because you can't evaluate other logarithms with your calculator. So using any other log other than those two would be really counterproductive. After this line, I move that exponent out in front, so I can do the exact same thing here. So log 230 equals x log 2. Then I want to get x by itself, so I need to divide log 2 to the other side. So log 230 over log 2 equals x. And then I have to evaluate that in my calculator. And the answer you should get is 7.845490051. And to 3 decimal places, that's 7.845. A few more examples. Solving exponential equations. And we're going to kind of see two different types of exponential equations. One where the bases are powers of each other, and one where the bases are not powers of each other. If the bases are powers of each other, you don't really have to use logarithms, so those are going to be one step easier, and you probably won't need a calculator for them. If the bases aren't powers of each other, then we're going to have to apply some logarithms the same way we did in the previous question. So let's start with the one on the left. 2 to the power 6 is equal to 8 to the power 3x. Now, both 2 and 8 can be expressed as 2 to the power something. 2 is 2 to the power 1, so I'm not really going to mess with that one, 2 to the power 6. But 8 is 2 to the power 3. Now we have to raise that still to the power 3x. When you have an exponent raised to another exponent, you multiply the exponents, so we end up with 2 to the power 9x. Now we have common bases, so if the bases are the same, then the exponents must be the same, so 6 is equal to 9x. I'm going to move that 9 to the other side, so 6 over 9 is equal to x, which is actually 2/3 is equal to x. No need for a calculator. In our second example, we have 27 and we have 3. Lucky for us, 27 can be expressed with a base of 3, so that's 3 cubed. We still have this x out there, equals 3 to the power 5. When you have an exponent raised to another exponent, we multiply them, so 3 to the power 3x is equal to 3 to the power 5. And now that our bases are the same, the exponents must be the same as well. So 3x is equal to 5. Get x by itself, x equals 5/3. Now let's move on to an example where the bases are not powers of each other. So in example number 1, 2 and 3, 3 can't be expressed as 2 to the power something, and 2 can't be expressed as 3 to the power something. So now we have to get some logarithms involved. So same idea here, we're just going to apply a logarithm to both sides. So log of 2 to the power x is equal to log 3. Again, I could have used the natural logarithms, but I just chose the common log. I'm going to move that x out in front using the power law. And then I need to get x by itself. So I'm going to divide log 2 on both sides. And then I evaluate this to get 1.5849662501. 43 decimal places 1.585. Now we have the same process in question number 2. Bases are not powers of each other, so we're going to have to apply some logarithms. Just because I can, I'm going to apply the natural log this time. So ln of 5 to the power 2x is equal to ln of 6 to the power 4. We're going to use the same power rule, so we put the exponent out in front in both cases, so 4 ln 6 over here. And I want to get x by itself, so I need to divide both the 2 and the ln 5 to the other side. So x equals 4 natural log of 6, and we're dividing by 2 natural log of 5. Then it's time to grab your calculator. 2.226565505 is what your calculator should tell you. And to 3 decimal places, 2.227. This one is really easy to mess up if you're not using your brackets properly. I would make sure that I have brackets around the 2 ln 5 in the denominator. And just one more example. So 6 can't be expressed as 3 to the power something, so we're going to have to apply logarithms to both sides. I'm going to go back to the common log now. So 2 times 6 to the power x plus 1 is equal to log of 3 to the power 2x. Now I actually have to apply a couple different log rules right here. On the left-hand side, I have a product. I have 2 times 6, and then the 6 has an exponent there. But because we have a product, I'm going to apply the product law, which says we can separate these with addition. So log of 2 plus log of 6 to the power x plus 1. And then over here, I have an exponent. So I'm going to apply the power law on this side. So 2x log 3. Now you might notice that I still have an exponent here, so I need to apply the power law to this logarithm. So the log 2 stays the same, plus, now this exponent gets written out in front, and it's important that we put it in brackets, as it's going to multiply log 6. Log 6 is going to be distributed through there. And 2x log 3 stays the same. So I am now going to multiply this log 6 through the bracket. So we get log of 2 plus x log 6 plus 1 times log 6 is just log 6 equals 2x log. Then I'm going to bring all of the terms that have an x to the same side, and everything that doesn't have an x goes to the other side. So we already have log 2 and log 6 on the left. I have an x on the right and 1 on the left. So if I move the, x log 6 over to the right-hand side, then I've separated things nicely. So log 2 plus log 6 is what's remaining on the left. And I have this 2x log 3. To move this over, I have to subtract it, so minus x log 6. Next, I want to factor an x out of these two terms. So log 2 plus log 6 equals x. If I factor an x out, I'm left with 2 log 3. And then here I'm just left with a log 6. Now I want to get x by itself, so I have to divide this to the other side. Now I'm going to show my work over here on the right just to keep it all in the same screen. So log 2 plus log 6. This stays here. Now I need to divide by this piece. So divide by 2 log 3 minus log 6. And that's just going to leave us with our value for x. And then it's a matter of turning to our calculator and plugging this in. And I get 6.128533874. We want to round this to 3 decimal places, so that's 6.128.